Hello dear students, welcome back to the channel and welcome back to the power system playlist. Here we discuss the very basic principles of power system and up until now we have seen what is a single line diagram. We have seen uh, what is a impedance diagram, what is reactance diagram. We also made an attempt to uh, represent the whole power system with the help of this single line diagram and we have tried to draw we have drawn this circuit of the whole power system using the impedance diagram and reactance diagrams. In previous lecture we have seen what is your synchronous motor, what is your synchronous machines, and we have seen about the power factor control of that synchronous machine. We have seen how do we control it. So today and after that we have also seen the power factor control in synchronous generator as well. Okay, so today we are going to see about the operating chart of this synchronous generator. So it would be highly recommended if you have already seen the previous videos about the synchronous machine and the power factor control of synchronous machine. It would be easier for you to grasp the concept because in that we have discussed the phasor diagrams. We have seen how does the synchronous motor works and how the power factor control takes place, how load angle changes. So it will be easier for you if you have understood that, but even if you have not, it will not be too difficult. Do I recommend you to watch it? So if you haven't, please watch that video. It would be flashing on the top right corner of the screen of yours in the I button. So I assume you have already seen it, and let's get started with the operating charts of synchronous generator. So firstly uh, you need your alternator to operate safely, right? If you are operating a synchronous generator, then you will definitely need your alternator's safe operation, right? And how do we achieve that? So what do? We define some boundaries within which alternator can operate safely, and that is done by capability curves. Okay, there are curves in the graph which define how your alternator can operate safely, and we call those curves capability curves. Okay, and how does this capability curve decides it? So it decides it on the basis of 4 points or four major things. Okay, so the first thing here I've listed that MVA loading should not exceed the rated MVA, right? So what actually happens when my alternator is loaded? Okay, I'm having some load. Let's say I'm having a load R. So I will be having some copper losses, right? I will be having some I square R losses, and because of that, what will happen? Armature will heat up, and when my armature will heat up, this will governs maximum MVA rating of my alternator, right? So, in order to avoid heating, in order to achieve a better performance, it is recommended that MVA loading should not exceed the rated MVA rating of my alternator, right? The second point is almost as similar as the first one, that my megawatt loading of alternator should also not exceed the rating of my prime mover, right? So if you have understood the first, second would be cakewalk. Then third point, important point, that field current should not exceed some specific value. How do we decide that? Let's see that. So if you have seen the previous video, you would be knowing that what happens when we increase the load, the terminal voltage of my alternator will decrease. Okay, this this drop in voltage or this decrement in voltage is often noticed more in the case of the machines which are operating on lagging power factor. Okay, and almost every machine which you will come across will be operating on the lagging power factor. So what happens, the field current is increased in such case to maintain the terminal voltage constant. Okay, so if your power factor is lagging and your terminal voltage is decreasing, you will need your field current to come and save you, right? So field current will be increased in such case so that we can get the we can not get, at least we can maintain the terminal voltage as it was, right? So this field current, when it is increasing, but we must have to take care of that it should not increase such that the value which has been specified, or the value which is there is some specified value, right? After that the heating may cause damage to my field winding. Then the fourth point, the load angle must be less than 90 degrees for steady state operation. So the power angle, or you can call it load angle, we indicate it with the help of delta. So it must be less than 90 degree for any of your steady state operation, right? Now let's come to the phasor diagram. You can see that in the figure. So if you remember from previous lecture, that what did we do when we were taking the reactance diagram, or what did we do when we were plotting the impedance diagram as well, right? We neglected the resistance. Okay, we neglected the resistance value because it was too less, because my power factor was in lagging condition. So when my power factor is lagging, my value of my resistance will be too less, and because of that, what do? We can neglect the IR drops, right? So we will only consider the voltage drop across the load, and then we will consider the drop because of the reactance, right? IX drop. This IX drop as well, we divide it in two components, the sinusoidal component and the cosine component, or you can call it real component or imaginary component if you are into mathematics, right? So let me first quickly give you a glimpse how do we plot this phasor diagram. If you have attended the previous lecture, it would be cakewalk, but either ways, let's uh, get done with that. So firstly, we will take the voltage across my load as a reference. We named it VT, right? Then again, we are running I'm running my generator at some load, and because of that load I will be having some uh, load angle, right? And that load angle will be delta, and because of that, what will happen, there will be some EMF will be induced. So it is, we are having this EMF here. Okay, now the current will lag this EMF by 90 degree exactly. So where you have drawn this EMF vector, the current will be 90 degree from this EMF vector. Okay, now here you have current, here you have voltage. So what will be this part? I mean, if I want to find how much drop I have to take the algebraic sum of my uh, these two vectors, right? So when did we do that? We got the value of Ia into xs, this vector. And what did we do? We simply put the tail of my Ia into xs vector right in front of the uh, face of my Vt, and this become your Ia into xs. Now what will happen? Remember, I just told you there are two components of each vector. You can call it sinusoidal component and cosine component. So we divided that Ia axis vector into its sinusoidal and cosinusoidal components. Okay, sinusoidal is always always lies on your horizontal axis or x-axis, and the cosine component normally lies on your y-axis, or you can call it vertical axis, right? So here you can see we are having ia into axis sine a. See, it is lying on the x-axis, and there is ia into axis cos phi, which is lying on your vertical axis or y-axis, right? So I hope that much is pretty much easily clear to you. Here they have shown the arc with a radius e for constant excitation locus, right? When I'm having a fixed delta and I'm not changing my delta, so at that time my e will remain this, right, on this locus. So now let's do something interesting. Now multiply each quantity with 3 into vp divided by xs. All the quantities you have seen here, let's try to divide it with 3 into 3 into v divided by xs. Okay, so what is v here? V is again supply voltage to the load. So we already had the load and we multiplied it with 3v divided by t xs. So what did we got? We got 3v square divided by xs, because voltage was already here. See, and same thing will happen with all other equipments. We had only emf here, then we multiplied it with 3vp divided by xs, right? Here we had ia into xs and we got 3vp into ip. After apologies, after multiplying it with 3vp divided by xs, right? And same happened with my uh, cosine and sine component as well. Okay, here we had ia axis into sine phi, and after multiplying it with 3vp divided by xs, what did we got? We got 3vp, axis got cancelled, ip got multiplied, and then we got sine phi. Same ways for cos phi. Okay, but now after multiplying everything with 3vp divided by xs, pay a close look towards this chart. Let's pay a close look towards this chart. What is happening here? Can you tell me what is this line AB is? This vertical line AB, what is AB? Can you tell me? Here it is mentioned P is equals to 3 VP IP into cos phi. So don't we call it real power or my active power, right? And what is 3 VP IP into sin phi? Don't we call it my reactive power, right? And what do we call this OB? 3 into VPIP. So don't we call it my apparent power or resultant power, right? So what is this triangle making? This triangle is your power triangle now. Okay, here you are having cosine value. Cosine value is nothing but your active power. Sine value of power, sine value of total power, it is nothing but reactive power. And here we are having the vector sum, or call it apparent power, right? Now after seeing this power triangle, let's let's come to some more so let's do some more interesting things. Okay, so let's come to this graph. Let's come to this graph. Here we are seeing the capability curves, which we have discussed in the beginning of the session, very beginning of the session, right? So uh, first let's start from O dash. Okay, so the stability limit is still delta is equals to 90 degree. Okay, so the line O dash M is this one. O dash M, this line is at right angle to O dash O. Okay, so the angle between O dash M and O dash O is 90 degree. Now why it is 90 degree? Because stability limit is 90 degree. Okay, so now what happens when angle is 90 degree and I want to find the power? So V will simply becomes I into XS, right? Because what will happen at 90 degree? What will be value of my cosine? It will be 1, so it will be V into V is equals to I into XS. Now the short circuit current at rated voltage is represented by OO dash, this part. Okay, and for constant current, what did we do? uh, Constant current I into XS, this part, here, what did we do is we will have this circular trajectory, or you can call it locus, right? Because what will happen, your value of your S will be constant, right? I'm talking about this vector, guys. Okay, the value of this vector will be constant, right? And because of that, its locus will uh, circle with the center, okay, as point O. And what will be the radius? See, radius will be OB, right? Radius will be OB. So because of this, there can be many different operating points on this arc. So you can see there are multiple operating points are given here, illustrated here, right? And for those operating points, uh, because what is happening here, see, if I want to take the if I draw a straight line over here like this, and then I measure the sine component and cosine component, so different reactive power and active power will be drawn, right? Even though my apparent power will remain as it is, but the value of reactive power and active power will change accordingly in order to make my apparent power equal. Okay, so respectively active and reactive power will be drawn, and the horizontal lines which are drawn from these operating points will cut the active power axis. See, the horizontal lines which we draw from these operating points will cut the active power axis. See, this is my active power, and it will cut my active power axis. And what do we do? Because it is cutting the active power axis, we call it constant power lines. Okay, and these constant power lines you are seeing here, we will be these constant power lines will be parallel to your horizontal axis, or your reactive power axis. These lines, constant power lines. Okay, so now let's talk about what will happen when we will provide some load, or when we will provide some excitation. So for constant excitation mode, as my excitation is very constant, which means my load angle is not changing. If my load angle is not changing, then the current is the supply voltage, the voltage across the load will be constant, right? And the generated EMF will be constant, and its locus will be a circle with the center. What will be the center of my what will be the center of this circle, right? It will be O dash. See here, O dash, and we are having B, right? This is my EMF factor. So what will be the circle? O dash B. Okay, then we have this different regions. So what do they represent? See, what do they represent? So firstly, how do they form? So firstly, we are extending this voltage, my voltage across load, On x-axis we are getting point A. Then we are extending this EMF vector and we are getting point B. See here. Then we are extending my apparent power. I'm getting point C. And active power, I will come to that. Basically, we are just taking the safety measure for 10 degrees. I will come to that. But firstly, let's discuss one by one. Let's first discuss the first region, region between A and B. This region we call it excitation limit or Emax region. And the operation of alternator in this region will be limited by maximum field current. So your maximum field current will limit the operation of your alternator. Basically, remember we were talking the four things which should be affecting your alternator or armature, right? So the first region, in that region what is happening, the operation of your alternator is limited by maximum field current. Then let's come to the second region, this BC region. This region is a volt ampere limit region. So what is happening here, that the MVA limit, what it will be, 3 into VP into IP, right? And what will be your IP will be maximum permissible current. Now let's come to this interesting region, this CD region. It is also known as power limit region. So in this region, as you can see, it is very clear that operation of my alternator or operation of my armature is limited by the power of my prime mover, right? It is limited by the power of my prime mover. Then this region which I told you that I will come to talk later on, this DE region is called stability limit region. And the this operation of this region will be limited by what? It will be limited by my stability. But what stability? My practical stability. And what happens in the practical cases, normally theoretically I told you in the very beginning of this phasor diagram that the stability in theory is 90-degree load angle. But because we take it some safety margin, because we need some safety margin, what do? We take the delta or load angle as 80-degree. So in actual practice or in real type scenario, what do? We take 10% margin for practical stability. Okay, and hence my DE is slanted here. See, it is not vertically perpendicular to my O dash O. Okay, so these were the different regions, and the complete operating zone of my alternator will be decided with this, right? How? So it will be like it will go somewhere like that, something like this. We will have OA, then AB, BC, CD, DE, and again EO, right? This will be my loop. And this curve is called operating chart, or you can also call it capability curve. Okay, and your operating point, at what point you are operating your synchronous motor or synchronous generator, sorry, synchronous generator must lie within this operating chart. Okay, so see, this is your limit of your armature, this is the limit of your alternator, and see this point B, it should be within this area which has been found by this curve. So as long as the point B of yours is on part of this area, is inside of this curve, your armature will be safe. As quick as my point B will exceed this area or surpasses this area or surpasses this curve, at that time my armature will be at risk. Okay, and also there are some benefits of this curve. So what are the benefits? So from operating chart, or what else did we call capability curve, right? So from operating chart or capability curve, we can also get the information about few variables, right? What can we get, right? So we can find whether the operating point is in stability limit or not, right? Because we are having stability limit point here. So we can find if my b is in under the stability limit or not. We can find the load angle, right? We can find delta load angle. We can find active power, reactive power, and apparent power very easily, right? We can also find current ia. How do we find it? So I, what will be value of my I will be 90 degree to my e vector, right? So by that, by doing that, by plotting that, we can also find my I. Then we can also find the var, right? We can also find the var, because we have v, we have I, so we can find var rating, right? And then we can also find my emf generated, or we can also find e. So uh, that was all about operating chart, or in other words we call it capability curve. And uh, what does it do? Basically it uh, provides you a curve with a limit within which your armature or your alternator can be operated alternator can be operated very smoothly or safely. And if you exceed that, your alternator can be at risk. Except that it also provides the variables or different quantities which we have just discussed. Now let's move on from operating chart to the last point of discussion today. We are going to see the different kind of representation of loads, right? So what are the different loads? So before going to that, uh, you already know that the utility supplies of power to variety of consumers across the the whole globe, right, will be different, right? And because of this different demands, we need different type of loads here. So let's quickly go through it. First is domestic load. It is the load which you get at your houses. It is the load which is used in the lighting of your houses, in the wiring of your houses. It is the load which is used for heating purposes. It is the load which is used to run small motors. Then we have the different second one, the industrial loads. So industrial load, the load which is used in the industry, the load which is used in the hospitals, the load which is used in the colleges, schools, right? Or any big organization, company. Such load is called industrial load. Okay, so what are the parts of this industrial load? We have large motors, large heating furnaces will be covered in the industrial load. Then we have agricultural load, or farming load. You can say whenever uh, we need to do that, all that farming work, all that agricultural work. For all that, whatever motor you need, that will be your agricultural load, right? And then transport traction load, the motor. Whenever you travel to the tram or electric bus, or electric tram or electric train. So all that load are the part of transport traction load. Now we can also see the type of loads with one another perspective, right? From we can see this these loads with analytical point of view as well, right? So let's try to see that. Okay, here. So what happens? The load on the power system changes over the entire day, right? And Because of that, what happens, the power system economics is largely dependent on the diversity of load, how quickly your load is changing, right? So it becomes very crucial to distinguish different kind of loads. So here we can distinguish in constant power representation. We can call another one the constant current, and third one constant impedance. So what do we do in constant power loads? We keep my active power and reactive power specified, and we consider my active and reactive power constant. Okay. So when you keep your active and reactive power constant, what do we do? You can uh, use it in your load flow calculations. Okay. So when we want to do my load flow calculation, we keep my active and reactive power constant. Okay. Then the second one is called constant current representation. What happens in that? The magnitude of the current remains constant. Okay, it's pretty much self-explanatory. So whenever you need to do the analysis thing, at that time constant current representation is used. And third one, which is called constant impedance representation. So when again self-explanatory, what do? You keep the impedance part constant here, right? So where is it followed? So mostly whenever you are doing stability studies, at that time you need that your impedance stays stable or constant, so we use this constant impedance representation at there. So stability studies, it is used in the stability studies purposes, it is used. Then the load specified in megawatt or even megavar at normal voltage is also used to evaluate the load impedance. Okay. So that was pretty much it from my side from today. uh, so in the next lecture we will be seeing more exciting stuff, but let's keep this lecture till here. If you have any doubts, any queries, or you want to ask any questions, if you have any feedback regarding the channel, regarding this playlist, regarding any other playlist, if you want to discuss anything with me, feel free to mention your doubts or any of your thoughts in the comment section below. And I will be seeing you in the next lecture. So till then, uh, goodbye, take care, and thank you very much for listening.